So previously in this module, we've looked at an important idea called independence. And that's when we had the independence of two events, meaning that one event didn't tell you anything about whether or not the other event occurs. So similarly, it's also useful to look at an idea of independence for random variables. So two random variables are independent if knowing what one of the random variables had as its value doesn't tell you anything about what the other random variable has as its value. So it's the same idea as independence for events, but we'll need just a slightly different definition. So as a reminder, this was the definition for events. Two events, A and B, are independent if you get the probability of their intersection by multiplying together through the probabilities. So we can have a similar definition for independence of random variables. And here we would say that two random variables, x, y, are independent if, and here instead of the probability of the intersection of two events, we have the probability that x takes on some value x and y takes on some value y. And again, we want the product that the probability that both those things happen to be the product of the individual probabilities. And this has to be for all x and y, by which I mean for all x in the range of x and for all y in the range of y. So we can actually write out this definition here using the language we learned in the previous subsection about joint and marginal probability mass functions. Right? Because on the left here, we've got the joint probability mass function, pxy, xy. And here on the right, we've got the product of the marginal probability mass functions, pxx and pyy. So that's our definition for independence for random variables. We can also actually extend this to more than one random variable, right? We have lots of random variables, multiple random variables, x1, x2, up to xn. We can say they're independent if we have the same thing about the joint probability distribution equaling the product of all the marginal probability distributions. So here this would be that p x of x, where I'm using x here to be the vector of all the x1 through to xn, is equal to the product. And the same way as that we write a big sigma for a sum, we can write a big pi for a product. But this just means multiply them all together. And then there we've got the probability mass function of the ith random variable. So if multiple random variables are independent, that means you get the joint distribution just by multiplying up all the marginal distributions. So if we go back to the coin tossing example we had at the beginning, is this independent? Well, let's just take x equals 0, y equals 1, so up here. So the joint probability there is 1/8. But if we look at the two marginal probabilities, they're a quarter and an 8. So the product of those marginal distributions is 1/32, whereas the actual joint distribution is 1/8. So they're not equal, and so this x and this y are not independent. It's not surprising, they both depend on the first two coin tosses, but we have therefore checked the definition, and the x and y we were considering there are not independent. There's one important place where this idea of independence comes up, and this is something we call random variables that are independent and identically distributed. That's abbreviated to IID, independent and identically distributed. And that means what it says, right? You've got a bunch of random variables, and they're all independent, and they all have the same distribution. So like you've got a bunch of, I don't know, Bernoulli trials. They've all got the same distribution and they're all independent of each other. And that would make them IID, independent and identically distributed. And this is useful because this is kind of how we represent sort of repeated experiments or something. If you repeat the experiment, then you would expect the outcomes to be independent of each other, but you would expect them to be identically distributed. This doesn't mean they take the same value, quite the contrary, because they're independent of each other. So let's just write that down. So IID means independent and identically distributed. And one way to write that out would be to say that the joint probability mass function is equal to the product of all the individual probability mass functions, because they're independent. But all these marginal probability distributions are the same. So we might call them Px, but note no suffix on the x. Xi. So compared to up here, we had the xi, because in the general definition of independent, all the PMFs could be different. Here, we just had an x, because all the PMFs are the same, because they're identically distributed, as well as being independent. Let's do a quick example of that just before finishing. So let's suppose that x1, x2 up to x20 are all Poisson 3, so Poisson distributed with rate 3, and they are IID, so these are identically distributed and they are independent IID. And what is the probability? They are all non-zero. Well, we can start by saying what's the probability one of them is non-zero, right? That's the probability that x1 is greater than 0, which is 1 minus the probability that x1 does equal 0. The probability that x1 equals 0, this is the Poisson distribution, so this is e to the minus lambda. Strictly speaking, it's e to the minus 3, 3 to the 0 over 0 factorial, but 3 to the 0 and 0 factorial are both 1. So you can just remember that the probability of Poisson distribution is 0, it's just e to the minus lambda, which is what I have there. And I typed that into my calculator earlier, and I got that that was about 95%. And although we've written that down for x1, because they're identically distributed, that's also true for x2 and x3 and x4 and x5 and so on. So what's the probability they're all non-zero? Well, because they're independent, we can just multiply up the probabilities for each of them individually, right? And because those are all the same, we could just use number 1 as an example and raise that to the power of 20. Right, so because they're identically distributed, x1, x2, x3 all have the same probability of being non-zero. And because they're independent, we can just raise it to a power because we multiply together the probabilities. So this is, this 0.95 number to the 20. And when I typed that into my calculator earlier, I got 0.360, the probability that those IID random variables, those independent and identically distributed random variables, were non-zero.